Okay, good morning. Today's date is the 25th of January 2016, and we are continuing our discussion on amplifiers. So in last class we had discussed the form of the Y matrix that will give us an ideal voltage controlled current source. So we saw that to get a nice voltage controlled current source implies that I want a Y matrix of the form 0, 0, some GM and another 0. In today's class, we will see and try and understand if a metal oxide semiconductor field effect transistor, also called as the MOSFET, we will see whether the MOSFET is a good voltage controlled current source or not. So the question we are asking is a MOSFET a good voltage controlled current source? In order to answer this problem, let us look first at the equations that govern a MOS device. So a MOSFET has a construction as follows. There is, for example, a p-type semiconductor into which two regions called the source and the drain are made heavily n-type. So I call that as n plus and an n plus to designate that these are n-type regions. On top of this, there is an oxide which I am drawing in magenta, and in modern MOSFETs the oxide is typically having a thickness of around 1 nanometer, and on top of the oxide there is a metal which I am drawing in red, and that I will designate as the M, or the metal, and this layer here is the oxide. This device is metal on top of an oxide which is top of a semiconductor, and the name metal oxide semiconductor field effect transistor. This is the cross-sectional view of this device. We can also look at the top view of this device, which would look something like this. Correspond to the source, you would have a region this, and then the gate, and then you would have the drain. So this would be the source, that would be the gate, that would be drain. So to make everything very clear, one can actually show where the source and so that would be the boundary of the source, that would be the boundary of the drain, and I have drawn it. It's not very well lined, so let me just check that. So the source region would be that, the drain would be that. Alright, so one can now actually dimension the various critical dimensions of this device. So one dimensions is the length of this device, and that given L, and all the gate length. So L refers to the gate length. The important dimension is called W, and which is referred to as the channel width. The ratio of W by L is called aspect ratio. MOSFET we have discussed in the previous has the following I versus V characteristics. Also, one should remember that we are interested right now in what are called the output characteristics. By output characteristics, we mean the following. We are interested in the situation where I plot DS, right, which is the voltage between the drain and the source on the x-axis, and look at the current ID. Right? A symbol for the MOSFET to complete the story looks like this. Right? And arrow is that is the gate terminal, that is the drain terminal. To look this as a two-port network, you can, for example, look in the following way, right? The common source configuration, because now the source terminal is common to both the input and the output ports. So in that configuration, be your V1, I have a current flowing in, which is I1, I have another current flowing which is an I2, the plus minus V2. So your V2 is identical to DS and your V is identical to capital G less. Just remember that this particular drawing, the currents and voltages refer to the total currents and not the small signal currents. So this is just looking at the MOSFET as a black box consisting of an input port and an output port. So if one were to plot the current ID, which is essentially I2, function of VDS, then characteristics would be called output characteristics, because they essentially plot quantities which exist on the outside of the circuit. Similarly, you have another set of characteristics which we will refer to by a name which will become obvious soon, wherein I have, for example, VGS on the input and ID on the output, right? And these, what do you think the name of this would be? You notice that VS is an input voltage, whereas ID is the output current. So this is referred to as the transfer characteristics. This connects the input port to the output port. Is that clear? Right. All right. So now we are interested in the in and the output characteristics. Let me go now to the next slide and show you these look. Okay. We have dealt these characteristics in the previous course, but just to recap, again I have my device drawn as so, with this being the gate, that being drain, and being this. Alright. In the previous class, we had discussed the current ID can be written in the following form. The first situation I will consider when the current 0, when the voltage VDS is less than another voltage called VT, and there is a name VT which we will write down here. So VT is called as the threshold voltage. Right. Then in the situation where VGS is greater than VT or greater than equal to T, two sub-conditions. I have to look at the drain source voltage, and if the drain source voltage is less than or equal to this difference VGS plus VT, I have one kind of expression, and I need more space. Okay. And in the situation where I have VGS greater than VT and VDS greater than VGS minus VT, I have a different situation. And what are those situations? Those situations are given as follows. This is given as mu soc double, I'll explain quantity in a moment, into VGS minus VT into VDS minus VDS squared by 2. And in the region where VGS greater than equal to VT and the drain source voltage is greater than to VGS minus VT, I just plug in the value VGS minus VT where VDS exists, and I will get the following expression: mu C ox W by 2L into VS minus VT the whole square. Alright? Okay. Now we need to give name to both these two regions, and that will become clear. We draw out the characteristics. Alright. First thing to see, we will consider this region where VG is greater than or equal to VT and VDS is greater than or equal to VGS VT. So let me take the situation of any one particular VGS. Let me call it as VGS1. So let me say I have value here, and that value is given VDS equal to VGS1 minus. Is that clear? Okay. Now, what will the value of current be? The current, let us say, is going to be something like this, and say that and because of, if you look at this expression, it is independent of VDS, and hence it has to be a straight line parallel to the x-axis. Alright, now let me increase my VDS to another point, and let me call that as VGS2 VT. Is that alright? So what is going to be the current at this value? If you notice, the dependence of current is quadratic on VGS minus VT. So if you are looking at VDS equal to VGS2 minus VT, you are going to see that you can actually obtain the point at which it becomes flat by drawing a nice parabola from here. We'll draw a parabola. Right? That's a parabola. So I have, for example, VGS1 minus VT there. To get VGS2 minus VT, I just come here, right? And for any voltage greater than VGS2 minus VT, I am going to be flat, and I will be in this region. Right? What about a third value? Right? What about a third value? I am out of space, so let me move everything down. Let me make some more space. Okay. Get to a third value, I basically have to extend this parabola, right, up there, and now look, for example, at another third value. So it's as high, say that the difference between VGS3 and VGS2 is the same as the difference between VGS2 and VGS1. So I have something that's there, and I'm going to be, I'll have a characteristic which is be flat for all values greater than that particular value, and this guy here is going to be VGS3 yes, VT. Note that this quadratic depends of the point at which at the point at which the lines become flat is quite important. All right. Now, can you give me a name for this region? Almost said it actually. Right? So this region is referred to as the saturation region because the V characteristic becomes flat in this region. Just keep in mind that the terminology saturation as used for MOSFET is actually a little different from the terminology that will be used when we discuss a bipolar transistor, and it's unfortunate, but that's the way names are, right? So don't get confused. We'll deal with the similar flat region for bipolar transistor when we get there, and I'll give it a slightly different name, and I'll also point out what difference is when we, okay? Alright. Now we are going to look at this scheme wherein you have VGS greater than VT, but VDS less than equal to VGS VT. How do you think the current voltage characteristics are going to look in regime? Right? So you know that VDS equal to 0, right? This current effectively goes to 0. so I have to be here, and you know that at this limit you have to this point, so basically you can connect these two via smooth. And this region has a name, and that is called linear region, and explain why it's called the linear region in a moment. So to the left of this red dotted line is linear region, and to the right of the red dotted line is called the saturation region. Okay. And what about the situation where VGS is less than VT? Well, when VGS is less than VT, the current is identically 0, so I don't need to worry about that, and I can just draw it as a thick line, right, sitting here, and that would be the situation for VGS less than V. Okay. And to just complete this curve, I can put down what the things are. So this is for VGS1, this is for VGS2, and this is for VGS3. And as I have drawn, I have tried to draw here, VGS3 minus VGS2 is equal to VGS2 minus VGS1. Alright. So that's with respect to the output characteristics. Remember that I still have to justify why I have called this particular region as the linear region. We'll come to that. Before we go there, let's just transfer characteristics. We have done this too in the previous, so we can do this quickly. Alright, the transfer characteristics look, right? If you go back, so the transfer characteristics essentially plot ID as a function of VGS, and if you notice for things less than so let me say this is my VT. For anything less than VT, I be at 0. So I draw that identically as 0. Okay. And then if you have VGS greater than V, then you can have two different regimes based on the value of VDS. Let me say that I'm interested in the saturation region. Then saturation region, basically I'm going to have a parabola, right? I'm going to have a parabola like that, correct? So this, just keep in mind, this is for the saturation region only. In the saturation region, current ID is independent of what? It's independent of VDS. Okay. I will, I will leave the situation where you are in the linear region as an exercise. We don't really need it for this particular course, so let's not go there. Okay. So why did we start doing all this? We started doing all of this because we asked the question as to whether a MOSFET good voltage controlled current source. And by a good voltage controlled current source, from previous lecture, we know that we are looking for a Y matrix, right? We're looking for a Y matrix. This is the element Y matrix, and we want an integral Y matrix which is for 0, 0, GM 0. The question we are asking is whether a MOSFET is a good voltage controlled current source or not. Alright. So, in which region do you think this MOSFET can behave as a good voltage controlled current source? Which of the regions? Is it in the linear region or in the saturation region? Okay. To see that, just calculate what the incremental matrix will be in these two regions, and let's conclude. And as I will tell you, you can also justify to yourself why this region to the left of this red dot is called the linear region from a similar kind of calculation. Okay, so I'm going to have this with me. Okay. Oh. And also I'm going to take this notion that we had of a MOSFET as black box, and I am going to put it here. Okay. What are my parameters? What is y11? This is the incremental parameter, right? So y1 is nothing but dou id divided by, am I right? No, I'm wrong. So nobody caught me there, right? It's dou I1. I1 is essentially my G, or the gate current, right? So the one current, and so this is gate current, right? So this is Ig divided by dou V1, and dou V1, V is VGS. And what is y11? Remember, these are the incremental parameters, so they have to be evaluated at the Q point, right? And this is 0. Is that clear? Because Ig we claim to be 0 in a MOSFET. Why is that 0? Because if you look at the MOSFET, then the gate current, right? This is your gate. Gate current, the capacitor there, right? So no D current can flow from the metal into the semiconductor. So your gate is 0. All right. That's your y11. Now let me go to the next term, which is y12. What is y12? Again, I'm looking at it, the saturation region, which is this, right? This is your saturation, and that is linear. All right. So what is y12? Y12 nothing but I G divided by dou VDS, right? And that is also 0. So far so good, right? We've got the first two. The first row, both at 0, right? Okay. Now let's go to the next quantity, which is y21, which is what we're interested in, right? y1 is nothing but dou I D divided by dou VGS. And what is this? Can you someone calculate this? Right? This is going to be mu Cox W by L into VGS minus D. And we are going to call this as being the EGM. Alright, I think I forgot it a couple of things, so let's just go back and let me fix that. In this equation, I did not tell you what mu, Cox, and I didn't tell you what mu and Cox are. So mu here is called as the mobility, right? The mobility of electrons in this device. It's a measure of how fast these electrons can move, and Cox is the capacitance of the gate. Okay? That is Cox. It's actually measured in units of, it's actually the capacitance per unit here, but let's not worry about that right now. So mobility, Cox are essentially and WL, right, are basically properties of the device, and then VGS and VDS are properties which you can change based on the bias, right? So let me just call quantity mu Cox W by L by, circle that, and call that quantity some K, right, just to make things easy. All right. So now if I come back here, this is essentially equal to A times DS minus. Now I also get, can I write this y21 in a different form? Here y21 in terms of K and ds minus Vt. I just mentioned that K is a property of the dis and VGS is a property of the bias, right? So can I now write in terms of the current? Is that possible? Right? It should be possible. Let me write down an answer and justify to yourself that is correct. So y21 also equal to 2 times Id divided by s minus Vt, right? And also equal to under root of, can you what the other expression of K is going to be? The other expression for y21 is going to be, so I'll have 2 times K into Id, right? So if you notice, I have 3 expressions for y1, which I am calling as the transconductance Gm. So I have this expression, which is a function of Vg and K. I have this expression, which is a function of Id and Vg, and have this expression, which is a function of K and Id. Okay, so you can use any one of these expressions. All right, and finally, let me write out the final parameter, which is Y21, right? Y21 is dou ID divided by dou VDS, right? And this, as we are looking at this only in saturation, right? I'm looking at this in the saturation region. In the saturation region, dou I by dou VDS, as you can see, there is no dependence of I on VDS, so that is it, right? In the saturation region, does the MOSFET behave like a good voltage control current source? Yes, right? Because in saturation, my Y matrix, which is my incremental Y matrix, is identical to 0, 0, and there's a kappa VGS minus VT, 0. Right? This is the situation in saturation. Is that clear? So, what have we concluded so far? The main conclusion so far is that MOSFET saturation is good voltage control current source, right? Okay, now let's now look at the linear region. I'm not going to calculate all of the quantities in the region, because you can go back and show for yourself that in the linear region the MOSFET is not a voltage control current source. But what I am interested in is a motivation for why the linear region is called the linear region, right? I've been mentioning that I will justify that to you. Let me just do that. Okay. So have my ID is equal to this, and this is in the linear region. Okay, and I'm only interested in following ratio, which is dou ID divided dou Vs. Alright, what is this? Remember, this region is given by VGS greater than VT and what? VDS less than VGS minus VT. Correct? So this region, this is nothing but K, because this quantity is my K, correct? Okay, K times VGS minus VT minus this would become Vs. Is that right? Okay, now let's look at the case where VDS is much less than VDS minus VT. Okay, or to look at it pictorially, copy the out characteristics and put them here. Okay, so let's look at the situation very close to the origin, right? Let me look at the situation very close to the origin. Then I'm going to have, then the ratio dou ID by VDS is approximately K times VDS minus VT. If you notice, this is dependent of VDS, right? So basically, I have a situation, I have a MOSFET, right? And this is my source, and that is my drain. I have that, and I have that, right? And I have applied a very small bias, right, between drain and my source, right? VDS is much smaller than VGS minus VT. Sorry, this should be VGS, right? That should be VG minus VT. All right. And this is it. So also, how is this biased? I have VGS, right, which is to that. Okay, well, this is a little unclear, so maybe I can try something fancy. Alright, so that is, this is VGS and that is VDS, right? Clear? Okay, so if you notice, your slope of dou I dou VDS is essentially independent of S. So what does this behave like? Right? This behaves like a voltage controlled resistor, because value of the resistance, right, is independent of VDS but depends on the value of VGS. So essentially, pictorially, you are working in this regime, right? So you can that or that, right, or like that. So depending on the value of VS, you get different values of resistance, right? And because this resistance, or this look like a resistance, this region is called the linear region. All right. Anyway, in this particular course, we will not really bother too much about linear region. We have to concentrate on the session region. Okay, so that's a lot of background into the MOSFET. And so far, what have we shown over the last few classes? What is it that we have shown? We considered the voltage controlled current source, and then we took the ideal equation and we said that we want an incremental Y matrix which has the form 0 0 GM0. Then we took the MOSFET, and then I have shown that the incremental Y matrix for a MOSFET working in the saturation region is indeed 0 0 GM0. Correct? So the MOSFET in saturation can be used to make a voltage controlled current source amplifier, and that's what we're going to do. Okay, so now comes the fun part, right? So now I will get to the fun part. So I'm going to write the MOSFET